Welcome to a final exam review session for ECE 442-542 in the spring of 2019. If you're playing along on D2L, you maybe have noticed that there was an additional lecture and video in unit or in module 8, and that was an example of a state space-based design. It's the paper and pencil and MATLAB material, and I think last night I jokingly said you would have 50% of your exam, final exam, dealing with MATLAB material. That was a joke, but it might be useful if you need to play with MATLAB after this class is over. Homework 8 is due today. That's extra credit, and that's on state space material. The homework is extra credit, but the material will be on the final exam. So the extra credit percentage-wise will just be like an additional homework problem set. So whatever that amounts to, I think we've had 7 up to this point. That's worth some fraction of your grade depending on whether you're in 442 or 542. Now I will just take that fraction, 1/7, and add it on to the end if you're looking for extra credit. There's some additional office hours starting tomorrow, and these are all almost every one is a 2-hour period except for the day that we have our final exam, and then it's only an hour and a half. Really you shouldn't be asking too many questions on the day of the final exam, but I will be there if you just need to dot your I's and cross your T's with some particular piece of information. The final is comprehensive. It's 15 questions, and those questions will be uniformly distributed. I would like you to bring your ID, a photo ID, to this exam. You will have 4 sheets of notes. You can bring a Laplace transform and Z-transform table. You can bring any of your drawing instruments, protractor, compass, straight edge, ruler. If you're now sketching root locus and you want to play with 2 poles to the right of a real 0, maybe that compass would be useful. You don't need it, but graphing calculators are allowed, but you know that no class notes, no books, no phone, and no computer. What I would like to think is you could read each of these outcomes and create your own set of problems for each outcome and work them all. And if you can do that, then you're prepared for the final exam. If you can understand these outcomes and create a problem associated with that outcome or multiple problems, you need to be able to work these problems forwards and backwards. If I've now given you a question on a previous midterm and it looks like you're going from A to B to C to D, think about what could happen if I ask you D and I wanted to get B. How would you need to approach that problem, or how would you flip that around to be able to solve it? So here are 24 topics. I said we would have 15 questions, so here's kind of a collection of possible questions, and I've even given you a practice final exam this semester. So you have a fair amount of information to be working with in order to prepare for the final exam. Let me just sort of scroll through some concepts. We started with modeling, and you need to be able to work your way around these blocks. If I now place you in one of these blocks, can you get to any of the other blocks? If I give you a set of difference equations, can you now give me a state space representation? If I give you a all delay block diagram, can you give me a transfer function? Or can you give me a state space representation? And some of these arrows connecting the blocks tell you how to go from one to the other. On the right-hand side, going back and forth, really the trick, the strategy is simply to label the delay blocks as your state variable components. And if you have a transfer function, maybe I will ask you some question that maybe is more related to Unit 8 material, state space design, and you're going, well, we never had it with a transfer function. Well, use this to get to a state space representation and work the problem. Bless you. Are there questions on this? You should be able to go from any point in the diagram to any other point. Similarly, if I give you any of these models and an input waveform, can you tell me something about the output that you would expect to see? And that output could be the structure, what are the modes, where are our poles, or it could be the complete solution. If I say a closed form solution, now it's not iterate to a particular value k or a particular value n, it's give me the expression that you can now plug in any value of k I want, or any value of L I want, and now I want you to, maybe I need you to calculate Y at time 16. You need to be an expert now at Z transforms and going back and forth between time domain and frequency domain, with whether those are signals or whether they are systems. And this, to get uniquely between those, you need to know something about the region of convergence. And the region of convergence now tells you sort of the structure of your time domain waveform, or the interval of support when it's valid. Is it right-sided? Is it left-sided? Is it two-sided? Is it causal? Is it non-causal? All of those can be determined based on the region of convergence. I apologize for this. Let me just state it up front. It's a beautiful unit circle, but you get the idea. What do you know about a region of convergence? That's a very vague question. But in this picture, what maybe is being highlighted or illustrated? Where are the poles relative to the region of convergence? Okay, the poles are never on the region of convergence, are they? The region of convergence is bounded by your poles. And sometimes you might have all of your poles interior to a region of convergence. Then you have a causal system if infinity is included in your region of convergence. If infinity was not, then you might have a right-sided sequence, and vice versa. Here we have a two-sided sequence, and since the unit circle does belong to the region of convergence, we know that this waveform, or the waveform associated with these three poles, is bounded. And that's this stability question, or that's how you could address that bounded or stability question point. Discrete equivalence. we have many different ways of going from a D of S to a D of Z, or from a G of S to a G of Z. The hold equivalents are assuming that preceding the system is a hold operation or a hold device, and I've tried to highlight that in this graphic. And typically we do a hold equivalent when we are trying to discretize a plant or a system, and that plant or system might be given to us either in frequency domain terms with G of S, or it might be described in a state space representation. And based on how it is described, you can either find the zero order hold equivalent in the frequency domain. Now you just find the Z transform of G of S over S. You just put another pole at the origin and find the Z transform of that, and then pre-multiply that by 1 minus Z to the minus 1. That's if you're finding the zero order hold equivalent for a transfer function based system. If you are working with a state space representation, then you pull out this exponential, this matrix exponential relationship. Phi is now e to the at, and gamma is this integral of e to the a mu post multiplied by the input matrix B. And if you physically, or if you need to computationally with paper and pencil, need to compute this matrix exponential, it may be more straightforward computationally with paper and pencil to do the inverse Laplace transform of Si minus A, that symbolic matrix inverted. And then you evaluate that at the time t of your sample period capital T. Sticking with discrete equivalence, we also talked about non-hold equivalence. The process of going from C of S to C of Z. And this might make even more sense if I had required 441, 541 as a prerequisite for this class. Then we would actually start with this concept. We would say, oh, remember the controllers you built in your analog control class, C of S? Well, day one we can design a digital controller. We'll now just discretize that C of S and obtain a digital controller. So when your boss says, oh, you're taking digital control, can you now give me a controller that we can implement with a processor, some kind of microprocessor or computer digitally? We want to get rid of this analog controller. Oh yeah, I spent one day and then I dropped the class, but I know how to find the discrete equivalent. That was when 441, 541 was the prerequisite for this class. Now we don't have so much that as a driving force, but we did talk about discrete equivalence. We didn't really say, give me a C of S, give me an analog controller. No, I sort of had to hand you that in this version of 442, 542, but you could now give me a C of Z. And in that case, we're just taking a signal and filtering it or processing it and producing another signal. We aren't preceding this filter or controller with a hold device. We just want it to be a signal processing system. And we could do that a couple of different ways, and even in the left-hand side with the numerical integration, we had 3 different strategies that we talked about there. Forward, backward, and trapezoidal or Tustin. And the PoleZero mapping, remember I could trip you up on that one with this single quote, usually. How can I trip you up there? Infinite zeros in C of S usually mapped into z plus 1 factors. Well, like on a previous exam, I might say I want to have a 0 at infinity in the C of z. That means now that you may not want to include as many z plus 1 factors. Question. The amount of z plus 1 factors we include will also influence the calculation of k. And the number, or the z plus 1 the question was, and the number of z plus 1 factors in our discrete equivalent will impact the gain calculation, and that's true. It does influence, because now if you had z plus 1 squared versus z plus 1, if you're matching gains at DC, you've now changed the scaling factor that k is going to need to be in your DC gain computation. Yes, it will influence your gain that you might need, and what gain you match will depend on the shape or the behavior of C of S. If C of S was sort of an all-pass filter, maybe it had a constant low frequency value and a constant high frequency value, you could possibly match at either location or at a central frequency, and your answer probably won't be that different. It'll be different, but it may not be that significant. Now we pull out our serial, right? Well, our box anyway of serial containing red hearts, blue circles, and yellow wedges. I don't know. Wedges are kind of have a banana flavor to them, so they're yellow. Hearts are naturally. Anyway, you know the drill, right? If you're interested in percent overshoot, then that's saying that that can be translated into a zeta value or a heart shape in the z-plane. If you are asked a settling time, then that might give you an R. And you should be able to go the other direction. You should be able to, if somebody you've now find dominant poles in the z-plane, can you tell me, based on that R and zeta, what the percent overshoot are or the settling time are, or in fact maybe what the peak time is. So you should be able to go back and forth with those. And I think I have provided a summary sheet in the final exam material module on D2L. And this tells you, this coaches you, here's your crib sheet. If somebody's calling this in from the sideline and they say, oh, you're given a settling time, T sub S. Well, you can now convert that into a pole location or a piece of the pole location. You can say how far away you are from the origin. Or if somebody now gives you a pole, you say, well, I can figure out how far it is from the origin. Based on that, I can find out the number of samples, the number of steps to get to my settling time. And so that's what this performance implies pole or pole implies performance is meaning. If you're given a pole, how does it perform? If you're given a performance, what's its corresponding pole? Similarly for percent overshoot, given a PO, what's the zeta? What's the heart that I should be thinking about? What's this logarithmic spiral in the z-plane? Or given that I'm on a logarithmic spiral, what's the percent overshoot? And remember, these are all rule of thumb. These are not precise. In the z-plane, we have a lot of zeros and poles, and that kind of destroys a lot of this, but at least this gives us a start as to where to maybe think about locating poles or how to anticipate particular performance behavior from your system. So that's available, and you need to be comfortable with that. So that's what I'm meaning by being able to understand and use this performance specification summary sheets. Yes?
Would you mind going over, so like on, I think it was the last exam, you gave us that problem where we had to find, I think, zeta, or the percent overshoot, and the radius, and shade in the region where basically they kind of intersect. You mind going over that?
So a question now from the audience is, what if you have a z-plane and you're asked to shade a particular region in the z-plane corresponding to performance specifications? And now you really just have to kind of pay attention to how it's worded, whether it says percent overshoot less than or percent overshoot greater than. I think that's where people were getting confused. If I now said I want a certain percent overshoot, and did I do that here? Wow. I wasn't a Boy Scout, but I'm prepared today. Now, I might say I want a percent overshoot of 20% or less. You would then look at this chart and say, oh, that means he wants a zeta value of 0.45 and what? 0.45 and what? I want the percent overshoot to be 20% or less. Which way do I want zeta? Do I want my heart to be collapsing or getting larger, my heart shape? If I want a percent overshoot of 20% or less, do I have... Yeah. Whew, boy. Let's just revel in this ability to anticipate questions. No. So now what do we have? We had zeta value of 0.45. And we want a percent overshoot of 20% or less. Which way would I shade? I would shade towards the bigger zeta value. So now I would be shading here. And if I said, oh, I want a percent overshoot of 20% or larger, then you would be shading what I didn't shade. And I need to be able to say that so that you understand which direction to go. And now if I said something about I want a peak time of a certain amount or less, now what does that put on top of this shaded region? What's the peak time tell us? That's our wedge. Oh, shouldn't have shaded that in yellow. I said my wedge was yellow, didn't I? Oh well. You'll cut me some slack. So now what do I have? I have a wedge here. And now if I want a peak time less then that wedge constraint determines which way do I want to sort of shade relative to a peak time of less than a certain value. Theta d now needs to be bigger, so now I would be looking at that. If I set a peak time of whatever that wedge is or less. Now if I said something about settling time, that now gives me a circle. And depending on what I say about that settling time, do you see how I could ask you to be in many different shaded places? If I said I want a settling time greater than what this blue curve indicates, that's, let's say, my shortest settling time, which way would I shade? If I now want a time to peak that's indicated, so it's bigger, a bigger theta sub d, I want a percent overshoot less than 20%, and I want a settling time larger than this amount. Which way do I shade? So now it's outside the circle. So now I would be, that region is where I would shade. Does that help with this shading? So you just start looking at one and kind of shading it, and then worrying about the intersection of all of the pieces that I'm asking you to put together. And I think you can see from this that I could ask you to be shading or ending up with an intersection region that's any of these different possibilities, depending on how the wording, and that's what you need to be careful with, what the wording looks like or how it's described. Hard part's getting back to where we were. Oh, wow. So there were, you know, this, wow, I already. So here is performance summary sheet, percent overshoot, dominant poles going back and forth. You can bring one of these if you want with you and hand that in with the final. Make sure your initials are on it if I'm asking you to shade something and you feel like you can shade it better on this. You could even bring in 64 color crayons. I didn't include that on your list of materials to bring to the final, but if you want to bring your favorite colors, feel free. I do have students in my other class, and they spend 30 minutes just sorting colors. Whew, try grading that one. Controller designs. What have we done? Well, Ragazzini was really introduced to sort of give you a way of thinking about constraints, or what you really shouldn't be doing with controllers, in terms of you can't be canceling poles and zeros outside the unit circle. You also need to be able to design root locus based controllers, and that's really now how do you pick poles and zeros to get your dominant poles in a shaded region in the z-plane. So putting all of these pieces together. And maybe I didn't make it clear last night, but I quickly was showing here's a challenging system to try to control. How did I come up with those 2 poles and a 0, I think, that I ended up with in that controller? Well, it was actually a state space based design. It was a full order estimator with full state feedback, the controller associated with that, and that now informed my concepts or ideas of where to sprinkle poles and zeros. You won't be held to that on the final, but you will be held to state space designs in the form of full state feedback and full state feedback with a non-zero reference input. So telling the system how to behave, you behave, and telling it where to go. Go to your room. And it will go to the room without any error if you pick your N1 properly. If you tell it to go to 2, it will go to 2. Just as a follow-through, though, we know that that depends very much on having a good model of your system. And so after this class, you may not want to just use that strategy. You may say, oh, I probably need to have an integrator in this system. And we talked about how to find that or how to set that up. You won't be held accountable for the integral control with state space feedback, but you will be held accountable to the I in the PI, the PID. What's an I do for you? Helps me see. No, the other I, the capital I. This is now the integrator, and that does what for us? What's an integrator good for? In a control setting. So an integrator works on errors in the past, and it accumulates that information. It builds up your error signal so that you're what? Really trying to squeeze that error to 0 now. It kind of makes your transient behavior worse, but now you're trading off maybe not as great transient behavior for steady state performance. Now, oh, I'm locked on to this constant input of 4.2. I'm right at 4.2 with my output because I included this integrator. With Ragazzini, we have constraints. What constraints are at play for this particular system, for G sub 1? In this case, we have R1, don't we? Restriction 1. Do we need to worry about anything else in building T sub C of Z, our desired transfer function? What is restriction 1? That says that the PoleZero excess in this desired transfer function, T sub C of Z, needs to be of at least 1. It could be 2, but it has to be at least 1. Why is that? Because you want a causal controller. That's what restriction 1 allows us. Anything else? Restrictions 2 and 3 are not applicable. And sometimes that confuses you as a student. You go, well, why'd you give us these restrictions if we don't even use them? Well, it depends on the plant that you're presented with. In this case, we have no open loop zeros outside the unit circle. So restriction 2 we don't worry about. And we have no unstable poles in our open loop system, so we don't have to worry about restriction 3. What if I gave you a different starting transfer function and I said, okay, let's deal with this using the Ragazzini approach? Or let's look at this one. What do we have to worry about here? What restrictions? So we need R1, our PoleZero excess, of T sub c of z must be at least 1. Do we need to worry about any others? We didn't in the last one. Now we need R2 because we have a 0 outside the unit circle. That means that z minus 2 factor needs to be a part of T sub c of z. So this is a 0 factor in T sub c of z. Anything else? We have an unstable pole, and we can't cancel that, can we, unless you want to get a minus 100 on your final. It's available to you, but I don't think you want it. So restriction 3 now says that you need 1 minus T sub c of z evaluated at z equal to that unstable pole location, which was 1.5. We need that to be 0. And that will keep our controller that we use that design formula for from having a 0 that will cancel that pole in our controller. That's what we're avoiding with this specification. And I didn't say anything about steady state accuracy, but I might have. I might have said, oh, I want a DC gain of the overall to be 1/2, or I want the DC gain to be 2, or I want the DC gain to be 1. So you need to be thinking about steady state accuracy and maybe that's translated into a DC gain so that we might need to know that T sub c of z is 1. Guess I was getting ahead of myself. What about PID controllers? Can you now write me a short essay on the benefits of I? That's the I in PID. That's now for steady state accuracy. And what's this? If I now said design a PID controller, what does C of Z immediately look like? Do you know anything about C of Z if I say PID controller? I'll do the hard part. I'll make it a transfer function. I'll put a line on the paper. What do we know about C of Z if it's a PID controller? So the I piece gives us the z minus 1 factor. The z, the pole at the origin, is to keep this causal, this controller, because now we have the ability to pick or to locate two different 0 values, beta 1 and beta 2. And beta 1 and beta 2 could be real, equal, real, unequal. They could be conjugates, complex conjugates of each other. We now have that freedom. And probably you would be guided in how to select those betas based on your knowledge of how to sketch a root locus diagram. What if I gave you the following root locus construction exercise. Suppose I said, okay, here's G1 of Z, and the numerator looks like the following: Z minus 1/4 squared plus 1/4 squared, and the denominator is Z, and Z plus 1/2 squared plus 1/2 squared. Can you see what that's presenting you with in terms of poles and zeros? Again, I will do the heavy lifting. That was the hardest part. Not really, was it? So now what do we have remaining in this Z-plane? We have 2 poles and 2 zeros. Any help on where those might be? So now I'm over here at minus 1/2, aren't I, for the poles, and J 1/2. So let me put those here and here. And my zeros. So those are there. What's the root locus of that look like? Or how would you maybe start to think about what rules or construction strategies you might need? Do we need to pull out our loaf of French bread? Does it matter in this problem? Do we have any branch or branches of the root locus on the real line? Which we're only cutting it in half, aren't we? The real axis. Which half? Positive half or negative half is on the root locus? So now we're there. How many branches of the root locus do we have? 3. How many of those 3 branches are going off to infinity? 1. Where are the other 2 going? They go to the zeros. So now if you really wanted to understand what this looks like, you may need to ask, what are the departure angles from the poles, and what are the arrival angles at the zeros? Suppose you now calculate the departure angles from the poles, and you find that the departure angle from the pole in the positive half of the z-plane is now minus 160 degrees. What's that telling you? Well, if it's 160, now it's coming that way, isn't it? And you go, okay, so, not sure how to continue. So you say, what's the arrival angle at the 0 in the first quadrant? And suppose that ends up being 180 degrees. Well, that didn't help me much. But can we determine whether or not those two branches that start on the poles, do they stay off the real line, or do they actually go to the real line and have a party? And then we know eventually one of those branches is going off to minus infinity. The other two are eventually going to these zeros. But what happens in between? Well, if these went like this, what would you know happens on the negative real line in the z-plane? What do you know is happening as we move from 0 to minus infinity? Do we know anything about that branch, or can we look at that branch and determine that, oh, in fact, we do have that behavior of our root locus as you've highlighted in yellow? How would we determine that? What's another possibility? What if these did that? What? Now, is that possible? So, what if we had the blue? Well, maybe I shouldn't do that. What if I start this one in yellow and that one in blue, and, oh, I need another one. And let's say this one. This guy is coming there, isn't he? So there are my three branches. I have yellow, blue, and green. What are you suggesting? Well, once these guys, one's going to go that way and the other's going to go that way, and the green guy is going to come here. Do you see what I'm suggesting? So that now this blue would hit the green, and blue would go there, and green would break away and go there. How in the world do we verify that this is the case versus the other case where we stayed away from the real line with those branches that originated at the two complex poles? Can we ask for some information that would verify this picture versus the earlier picture on our root locus behavior? We have the start and the end from the angle of departure and angle of arrival. What other piece of information might we use to determine that, wow, we do have this pretty graph, or this pretty root locus? So the phase angle condition can be used, but now that's going to be kind of tedious, isn't it? What's the phase angle condition going to tell us? That's saying that any point along the root locus has to have a phase of 180 degrees. So now we could compute, I shouldn't have done that, huh? That looks like a 0. I don't want a 0, I want a shape. So at that value of k, you could say, oh, I'm going to see, is this upper triangle on the root locus? And you would calculate the phase at that point, contributed by all the poles and zeros, and what would convince you that that triangle indeed is on the root locus? If you sum up all of these angles due to these poles and zeros, and you end up with minus 180. And then you could go down a little closer to the real line and say, oh, what about at this point? And that can't be going very fast to the left, that triangle and box, because it has to wait for blue to catch up. That should be giving us a clue. What's happening when those boxes approach the real line? What happens at that point on the real axis? What is that? What do we call that? That's the re-entry point. And what is that point relative to K? It's a relative minimum, isn't it? So now we have a relative minimum of K at whatever this is. Let's say -1. Then K increases. I'm now going blue. And what happens at the point where the blue and the green meet? What's that point called? A breakaway. And what happens at breakaway? Relative max. And then if I go further to the right, what's happening to K? It's decreasing, isn't it? Because I had a relative max at that point. Do you see that if I just graphed K, which you have a formula for K based on these poles and zeros, if you evaluated K from 0 out to -2, if this picture is true, you would see K hit a relative max, then it would start what? Decreasing now to a relative min, and then it would go in, and then it would just go unbounded. What would the other picture look like? So there we have a relative max followed by a relative min, and then it just goes monotonically big. What would happen if the earlier picture was true? We didn't have a re-entry, we didn't have a breakaway. So what happens on the negative real axis as we look at K? We just have a monotonically increasing K. So now if you sketched K as a value from 0 to 2, -2, and it was monotonic, you would say, oh, I had my earlier root locus pattern. If you sketched K from 0 to -2 and it had a relative max and then a relative min and then it starts getting big, oh, I must have a breakaway and a re-entry between 0 and -2. That might be easier than the phase angle condition, because the K formula, you just have to plug in real values of Z and evaluate it. Now, hopefully the relative is discernible. So you have to have a relative min and a relative max on your way to then growing unbounded as you go bigger. What if I gave you, that was so fun, let's do another one. Do you see what I was trying to tell you? How you could maybe check that? But on the final, I might ask you to find a re-entry. I could ask you to find a re-entry point, or I could ask you to find a departure angle or an arrival angle for some pattern like this. What if I gave you this transfer function? G sub c of z is z minus 1/2 squared plus 1/2 squared all over z Is that what we have? And what's our root locus look like? What if the arrival angle at those zeros is 185 degrees at the one on the first quadrant, or minus 175? We're now coming in like this. And suppose that the departure angle from the pole in the second quadrant is minus 20. Do Do you believe that? Do you know how to check it? You could just evaluate k from 0 to -1 and convince yourself there's no relative max or relative min anywhere there, so I didn't re-enter or break away on that segment of the real line. And that's just using the magnitude condition for k. What about if we do a z-plane controller design? Suppose now g of z is z minus 2, z minus 1.5. Probably getting tired of this one, aren't you? Is that what we have? How do we deal with this problem? I'd probably be asking you to stabilize this controller. I'm sorry, stabilize this plant with a controller. Can it be stabilized with a constant gain? No, I'm stuck between, oh, I didn't label this, but I'm stuck between 1.5 and 2. So now, is this what you do? No, you know better than that, right? We can't cancel that, and we can't cancel this, can we? So we can't do that, but we can put poles and zeros outside the unit circle. That's okay. We just can't use them to cancel something. So what would you propose? There's a lot of different possibilities, but we need to somehow get rid of this branch. How many root locus branches do we presently have? 2. If we add in another pole that doesn't cancel a 0, we may end up with 3 branches of our root locus. We're plotting with our root locus g of z's poles and zeros and c of z's poles and zeros, however we introduce those. Well, one way to possibly get rid of that segment, all of that segment between 1.5 and 2, is to put a 0 in there. But we did keep some root locus there. How many branches does that segment represent? How many branches of the root locus are on that real line segment? Let's say it's 1 3/4 to 2. How many root locus branches? And can I just be done with a 0? No, I have to put a pole in, don't I? Where would I put a pole? What? So what's happening between those zeros? I'm not done, am I? This is how I finish my root locus. I'm terminating at least how many branches in that segment of the root locus? 2. I have 2 zeros, finite zeros. That's where I terminate 2 of my branches. Right now I only have 2 branches, but I have to have a third because I've already put in a red 0, and I have to have a corresponding pole, at least one more pole input into this system to provide me with a causal controller. Well, if I put a pole here, Is that any good? Probably not. I'm going to have a breakaway, and they're going to probably want to go right to that segment between the zeros. So that's probably not a good choice. How about if I put one there? Maybe. What's going to happen now? What pieces do I have now belonging to the root locus that are part of my root real axis? Now, am I done? I have a breakaway and a reentry, don't I? At least. And what would you hope? You hope now that you're, well, I'm not going to answer that. You answer it. What are you hoping is true? Now you're hoping that you break away to the left of 1. If that's the case, then at least you can stabilize this system with this controller. So let's assume that that's the case, and now we have a breakaway. How would you determine? And on the final, I might just say design a stabilizing controller. That doesn't mean I ask you to find all values of k where this design is stable. I just want 1. And so now you might just say, oh, let me pick a pole. Let's say that I say, oh, I'm going to put my closed loop pole right there. And you calculate the gain to get you to that point. And then what would you want to do? What could you do to verify that that is an okay value for a closed loop pole? What are you needing to check beyond just saying, oh, I'm going to pick a K to get me there? Which pole, I'm not going to do any more because I'm going to give you the answer. Which pole now is at the triangle? Now it might be helpful for all of your 64 colors. We have this going there. We have this going there, and we have this one going there. We have 3 branches. Which pole is at the triangle? Green, yellow, or magenta? Green. So where's yellow? It better be inside the circle. Could we check that? How? I don't have a fancy calculator. I can't find the roots of this cubic. Okay, think a little bit more. How can we verify this? Can we? Can we verify that yellow is to the left of 1? Can we find a gain k that will make, if this picture is true, if the breakaway is in fact to the left of 1, then what can we do? Can't you find the gain at 1, the k at 1? And if you were lucky, you might find that you end up to the left of 1. But let's say now that you do this. Well, shoot, that's not really what I wanted to do, but I'm not going to try to erase it. Suppose you calculate the gain k at 1. And let's say that it is less than the k at the triangle. I am going to erase it because I have 2 triangles and I don't want 2 triangles. Suppose you calculate the k at 1, and this is less than the k of triangle. Does that tell you anything? What's that tell you about the triangle associated with yellow? Granted, I haven't had a lot of sleep, so I may not be thinking clearly, but you can help me here. Where's the triangle associated with yellow? To the right or to the left of the square? So now if K box is less than K triangle, then we know that the other triangle of yellow is to the left of 1, don't we? So this is a good thing. Are we done? Here's what I didn't want to do before. You have to worry about what's happening to that third pole, don't you? What do you hope is happening? You hope that the gain to get you to -1 is bigger than triangle. If it's not, you're going to have to back off the gain and hope that the gain for box is less than the gain at -1. Is that clear? If that's the, so you would be now saying, oh, he needs a stabilizing controller. Let me just check triangle, that point. Okay, there's my answer, but I need to verify that. Now you would check the gain at box and the gain at diamond. And then you would say, okay, this is going to work. Or you would say, whoops, it didn't work. I now need to back off. And hopefully K box is less than K diamond. If it is, then you can say, okay, maybe I cranked up the gain a little too much to get me to triangle, because that now sent diamond beyond -1. Do you see how to maybe think through this process? And how could you determine, well, you also have clouds. Those are going to go outside the unit circle eventually, aren't they? And so K cloud might be less than K diamond. And so your range of K for stability might be influenced by box and cloud versus box and diamond. But you now have those concepts or ideas to help you process. Yes? Can we determine the position of the cloud? Can we? The answer is a qualified yes. On the final, maybe not. But you can. How would you verify if cloud is on the root locus? You just told me phase angle condition. You could say, well, I think this is about the place where, but you know that those curved lines are not necessarily circular, right? Because that's not 2 poles and a 0. This is now 3 poles and 2 zeros. All bets are off. Yes? What was the comment? Put a pole between the poles. I thought that's what we did. Oh, without a 0. So now the question was, wouldn't it have been easier? Now I've forgotten what I had. Well, that's pretty bad. I told you I'm going on a little sleep. What did you just say? A pole between the poles? Does that solve it? Why did we put that 0 down to begin with? I better remind us where we're at. That doesn't help, does it? Because we're stuck between 1.5 and 2 with that branch. No, we don't break away from 1.5 to 2. We're just locked onto that real line with a branch of our root locus. If you looked at K between that, what's going to happen? K is going to just be monotonically increasing from the pole to that 0. Even if you break away, so you're saying you're breaking away here. Whoops, how did I get black? That's true, but how many branches now do you have going off to infinity? 2. And where are 2 branches that go off to infinity going? Plus and minus 90, aren't they? They're not re-entering, they're just breaking away and not going where you would maybe want them to go. So that's why we started with a 0, and then we said, well, we can't just put a 0, we have to put a pole down. That's the reason for that. So this one, ineffective. But that's what you need to do. You can just start sketching these and saying, okay, what's happening? That's why you need the understanding of the root locus construction. You can say, okay, what's happening here? How many branches do I have? 3. How many are terminating at finite zeros? 1. Oh, I have 2 branches going off to infinity. Though that means I'm at plus and minus 90 degrees eventually. And you could find the sigma and the asymptotes for that if you wanted to. That's probably not necessary, because now you say, oops, that's not what I want, and just exit off. You also need to worry about, I'm not going to be involved with the final, it's just you, state space design. I slipped and said we, but we in terms of the class, I guess. State space design. Full state feedback. U of L is equal to minus K X of L. But before you, and this is to change the behavior of your system. Tell it how to behave. And you know how to be guided. Now you can sketch regions in the z-plane. You can shade regions in the z-plane and say, here's where I want my dominant poles. And your other poles that you want to be faster could all be at the origin, for example, if you had 8 poles. But what is going to allow you to change the behavior arbitrarily? What's one check that I might have you do? Controllability. You need to be able to create the controllability matrix and determine if it's full rank. And if we have one input, now you just have to check the determinant of your controllability matrix. And you're now going to say, oh, I have a polynomial based on, or that's a function of k, and I'm going to set that equal to my desired, there's your shaded region in the z-plane. That delta sub d has some of those dominant poles as a part of it. And phi sub c is now the original, or the open loop system matrix, gamma k. The other piece that you will be responsible for with state space design is now if you have a non-zero reference input. And with that, you're telling the system where to go. Or now U of L, you've now enhanced it a little bit by having this non-zero reference input signal. and you can find the closed loop transfer function, which is now h zi minus phi sub c inverse gamma n sub 1. And you can use n sub 1 to adjust the DC gain of that transfer function. Questions on that? And you know there is a practice final on inside the D2L module for the final exam. And I would encourage you to look at that, and then based on your performance on that, that will guide where you need to focus more of your time in studying for the final. Yes?
I have a question on the Ragazzini control design. We did an example with real poles in the plant. So if we had complex poles, we just have to look at the magnitude and see if they're unstable or stable based on their magnitude.
Yes, so now the question was, what if during a Ragazzini design we had complex conjugate poles or zeros? Then yes, you need to make sure that they are inside the unit circle. If they are not, then you have to include that factor in the numerator if they corresponded to zeros. If they corresponded to poles, then you would need that 1 minus t sub c of z evaluated at that conjugate location was equal to 0. Yes, you would need to now enhance or grow the numerator, or maybe, yeah, probably even the numerator again if you have this 1 minus t sub c of z constraint on unstable poles.
But when we design a controller, then they don't really cancel off like when they were real poles.
So when you would now design for a Ragazzini approach, that's now going to allow your controller not to cancel unstable zeros that are complex conjugate or unstable poles that are complex conjugates by satisfying restriction 2 or restriction 3. And that's the point of those restrictions, is to try to prevent you from having your controller canceling something outside the unit circle. But we know we can place poles and zeros outside the unit circle. We just can't have those placed on top of poles or zeros. Other questions? If not, I will see you in a week. A little bit earlier than this. It will be at 1 o'clock, I believe. Isn't that the time of our final? 1 to 3 next Thursday. Good luck with your finals. I will see you in a week unless you see me in the hall or at office hours.